going to speak to the lovely Grant Stevens, who's from Fastly. He's a staff engineer at Fastly, and he's come from Perth in Scotland. Now, as a Scotsman, obviously, Scotland's very dear to my heart, but Perth is even more dear to my heart because my mother was born there. Oh. There you go. That's got nothing to do with programming. Grant is going to be talking about Go channels slowing down with more CPUs. And I've spoken to him several times, had supper with him. He's a lovely man. So I shall put you in the very safe hands of Grant Stevens, the man from Fastly.
Thank you very much, Donald. As you can immediately tell by my accent, I'm not actually Scottish at all. But I do live in Perth at the moment. So the first session after lunch on the final day of the conference, I realize I've got some work to do here. There's like a very real risk of people falling asleep. But we'll try our best and keep everybody awake. That's me. I'm Grant Stevens. I work in the logging team at Fastly. I used to be a mechanic, and I recently bought a chainsaw. Got nothing to do with the picture next to it there. As I said, work at Fastly. Fastly is an edge cloud platform. If some of you here use it, the sponsors do. And what that means is that we deliver your content from the edge to your customers, and so put less load on your servers. To talk a bit more about our edge, we have about 5,000 edge cache nodes in 35 different countries all around the world, and a capacity of around 300 terabits for our network. That's just sort of going out to customers. There's obviously back channels and stuff that goes on top of that, but yeah, that's Fastly sort of in a nutshell. And obviously today we're talking about Go channels and like how they slow down with more CPUs. But I thought I'd sort of set a bit of context to all of this, or put in a Go form context.background kind of thing. The one that you use when you're not quite sure where to start. You just start with the background context. Right. So, many of you might write an application, or maybe you do even for work, and it looks something like this, where you have a bunch of users, and you have some infrastructure that's running either on a server somewhere, on somebody's cloud server, or something like that. And that's all great, but you can see that like each of your users obviously hits your server directly, and sometimes you don't need all that load, and you've got to like keep on scaling up your instance or something along those lines. And so this is where Fastly comes in, and we say, well, a lot of that content doesn't actually need to come directly from your server. It can be cached somewhere. And so that's where Fastly comes in. We say, well, let most of the cached content be served by us, and only the requests that really need to actually hit your infrastructure. And so that's where the content is then served from the edge, so a server closer to your user. And you get a whole lot less load on your server. Your users get a better experience because the content's fetched directly from a server that's closer to them than your server that might be located in your basement. Cool, so that's sped everything up a bit, and you have less load, and it's all looking good. But we can do even better than that, and we can say, we do this thing called shielding. So say your server is located close to London, you can set your shield location to be London, and then all of our other edge cache servers will then first go and try and fetch the content. Obviously, they'll first check if they have it themselves. If they don't have it themselves yet, they'll then go and fetch the content from your shielding location, which in this case would be London. So there's sort of like a centralized point. And then the London one, if that doesn't have it, that's the only one that actually hits your backend at the end of the day. So even less load on your servers. You can have a super cheap sort of VPS instance that serves huge amounts of traffic just because like most of it's static, and we can cache that for you. Cool. There is, however, a problem here in that suddenly you have a whole lot of requests that are hitting infrastructure that is not yours. And how do you know like what's happening with those requests? Are they all succeeding? Were they 200s? Were they 500s? Maybe there's 404s. Like, you need to know all of these things. So what we allow you to do is to log So from all of these 5,000 different edge code cache nodes, you can send a log, and we forward all those logs for you, and then you can put them into your infrastructure, be that Datadog or S3, or there's 20 different kind of endpoints that you can define. And so all of these logs get aggregated together. In the case of S3, we'll bunch them all up and give you a zip file with some of your logs in them, and then forward those on to you. So maybe some of you have spotted it already, but there's obviously a lot of things going into that little sort of logging piece at the end there, and then sort of a single hop that goes over to your infrastructure. And you might notice some sort of like coming together there, foreshadowing. And just to put some names on these things, those things there we call the aggregators. So they're essentially aggregating all the logs from all the different edge cache nodes, aggregating them together. They don't actually do any processing on them other than sort of combining them up and zipping them up if you ask for gzip or things like that, retrying if your server happens to be down for a little bit and things like that. Right. To add even more context to this, these are some of our customers, and some of them obviously will use logging, and there's obviously some sponsors here which will make people happy. And there are obviously some services there that you probably use every day. So you're probably using our infrastructure without even knowing it. The common joke with CDNs is that you only know that something's on a CDN or know about the CDN when they have a really bad day and half the internet doesn't work. Cool. In terms of logging specifically, we're doing 36.9 million logs per second on average through the day. So that's sort of averaging out all the peaks and troughs for different traffic stuff, different traffic swings through the day. And from that, you can sort of see, OK, there's clearly some value here. People are using this. They need these logs. Like, that's a lot of logs to be passing around. So I hope that sets some context as to like where this fits into Fastly infrastructure and how it all fits together. Now we get to some of the more channel-based stuff. And one day it got slow. But that's also not quite true. It's more that it stopped getting faster. So the graph sort of went up and then just flatlined and made like a Table Mountain kind of thing, just flatlined over the top. And so we've had plenty of presentations this conference so far about debugging and stuff like that. So where do you start off? As Matt from Cloudflare, we can be friends, we start off with looking at the logs. And yes, the logging system logs itself. No, it doesn't use the same pipeline because then like both could be broken at the same time. So we start off in the logs. And after a lot of log diving, we're still scratching our head. And we can't figure out why this thing just won't get any faster. There's clearly customers are still trying to send more logs, but we just can't get them through them quickly enough. So generally speaking, my next port of call when there's nothing in the logs and you've checked all the metrics, a bit more about metrics. Breaking news. As from the previous presentation with Bartek and Ariana, with all the metrics that you can get in Prometheus, there's actually now a new metric that's been added in 1.23 that'll actually give you the wait times for mutex locks, and not just for mutexes that you write yourself, but mutexes in internal packages. We'll get to that a bit later. Anyway, so that would be one of the metrics to look at that might describe this problem, but as that only got released on Tuesday, we haven't really done that in production yet. So taking a step back, the old way of doing it is to profile it. And we still run this in an old school way, so we still use a good old SSH, simple one-liner there to grab a profile from a badly behaving host through a Bastion host, through a Bastion host. And this will grab the profile, and then you can do all your processing and analysis of it locally. And when you're doing that, and you have a look at one of these hosts that's sort of flatlined, you see this thing pop up. For those of you that have looked at traces before, have maybe seen this before, but the first time this popped up for me, I had no idea what that meant. And it's in the runtime package, firstly, so you're sort of saying, well, it's not my code that's slow, it's the runtime that's slow. But like, you shouldn't say that. That just feels wrong to say. So after a bit of Googling and reading on Stack Overflow and stuff, eventually it sort of comes out that maybe this could be a channel that's causing that. And then you sort of like, but there's like a select lock there. So the question then suddenly comes, wait, hang on, channels have locks? And then you do some more reading and you read some of the source code, and yeah, channels definitely have locks. They're optimized locks, and they're not like your simple mutex.lock that you would normally use, but deep in that source code, there's locks. And so when you're learning Go and you're getting to grips with it, everybody's like, just use channels, they're fast, they're great, it's all good. But under the hood, there's no magic. It still actually has to lock up when you need to put a message in and take a message out. OK, so that was an eye-opener. To put this in a bit of context, what this ends up meaning is that we have a single channel bottleneck. So we have all of these streams of data coming in from all of these 5,000 different edge cache nodes. And luckily, they don't all try and go into one channel, because obviously that would be an extreme bottleneck. But we did have one channel per customer. And what ends up happening is that some customers log a lot. Well, they have a lot of requests, which just means even if they're logging a small fraction of those requests, they're still logging a lot. And so, hang on, does that mean that can channels be that slow? So then you start going, but channels are fast. When you're learning Go, like everybody just says, use channels, they're fast, don't worry about it. Like you're never going to hit the limit of how fast channels can be. So when we started looking at this, you suddenly go, maybe I should Google this. How fast are channels actually? And there's a guy called Phil Pearl. Some of you may have heard of him. If you haven't, go and Google him and read a lot of his articles. He writes some amazing stuff and deep dive analysis into all types of things. Anyway, the first article that pops up is obviously something from Pearl, in my experience, from Phil. And so just how fast are channels anyway? So obviously Phil has hit something in his work and he's found it and like done some analysis on it. And when you read that article, all Phil did was wrote a basic benchmark, send 1 byte, do nothing with it, see how quickly you can do it. Simple as that. And I mean, he says a lot to it and does some comparisons with other things and just using a buffer and so on. But at the end of the day, Phil finds that channels are fast. There's about 10 million messages that you can get through a channel a second. So if you remember to a few slides back, we were sort of saying, OK, we had about 36 million messages a second, and this is 10 million, that's lower. But obviously, we have more aggregators than just one. There's a few more than that. So the 36 million is a combination of all of those. 10 million should be more than enough for one customer. So what's the problem? So we do some more head scratching. And we're like, OK, so we've got a benchmark of a channel. That seems to be fast enough. But those benchmarks are all run on our sort of local laptops. We haven't been benchmarking on production hardware. Would that possibly make a difference? So let's talk about these aggregators a bit. So the edge cache nodes are, as a colleague would put it, the biggest fire-breathing dragons we can buy. And they live all over the edge. They last a certain amount of time, and then they get handed down to other parts of the business that need them, which happens to be logging. We don't need the biggest fire-breathing dragons anymore. We can have last-generation fire-breathing dragons. So the edge cache nodes from a couple of years ago is now what we are using as the logging aggregators. And so when you look at the specs of those machines, they generally come in at about 128 cores and a terabyte of memory. So plenty big enough for doing logs, but maybe not big enough for doing edge cache kind of things. Now, some of you may have spotted this, the discrepancy here in that my laptop has 8 cores. I'm guessing some of you maybe have a few more, but 128 is not equal to 8. So could this be causing the issue? So, bright idea, let's benchmark on production hardware. Cool. So to expand this talk and make it more than just the 15 minutes that it is so far, I decided let's add a few more benchmarks. And we go and do a range benchmark and a select benchmark so that we can just sort of see what difference does it have if you're doing a channel with range versus reading off a channel with select. Cool. Quick side quest. Benchmarking tips and tricks. So firstly, if you've never written any benchmarks, learn how to write benchmarks. Dave's sitting in the front row. This is his article. It's kind of like the go-to thing when you're starting. Go and read it. Awesome resource. Great place to start. Cool. Next. This is something I learned along the way. You can build a binary that contains your tests. So this doesn't run the test, just creates a binary, which you can then copy over to your production hardware so that you don't have to have all your source code living on production hardware to run your tests. So cool, we can build a binary that just contains the tests, and off we go, and we can go and run those in multiple different places. So it's cool if you like, well, it works for me here, what's your performance on your laptop? And you just build them one, assuming they're the same architecture, but that's getting, anyway. Then, something else, which is super handy, is you can do a -test.cpu. And you can see there that we have 1, 2, and you can keep on going with that and go all the way up to 128. I didn't do 1, 2, 3 all the way to 128. I skipped a few in the middle, but the general principle of it stands. The other important thing there is the test.count. So maybe there's other stuff going on the server. Maybe you just want like a statistically significant number of tests to have run. So you do generally more than 6. I chose 10. I didn't want to be there all day waiting for this thing. Cool. So now we can run benchmarks on production hardware, and you end up with this very big file of test results. Turns out there's something that can help you with that, and it's called benchstat. Benchstat takes an old benchmark and compares it to a new benchmark, and you get this great output that tells you what the old one is with whatever statistical significance, and the new one, and then tells you what the change between them is. So when you're doing this for 128 different for CPU counts that keep on increasing all the way up to 128, benchstat saved me a lot because I didn't want to average out all the text files by myself or try and do something in Excel to sort that out. So, side quest complete. We now have benchmarking tips and tricks, and we've made our lives a whole lot easier. Cool. So, back to the benchmark. We have a range benchmark, we have a select benchmark, and we're on our way. So, we run that benchmark, and we get that. We send some bytes on a channel, we read them off as quickly as possible. The left-hand side is the number of messages per second. That's the label on that graph, and the bottom is the number of CPUs. All the graphs going forward will have the same legend on them. So it's number of messages per second and CPUs. You can see there that loop is twice as fast as the select, and increasing the CPUs makes no difference. Thank you very much. I'm joking. Obviously, there's a problem. Let's try that again. So we have a basic benchmark. This is my basic benchmark. Some of you might have spotted the problem here. We're testing this for multiple CPUs. If we're doing multiple CPUs, we have to benchmark in parallel. So a for loop for benchmarking is not going to do it. We need to do a parallel run. And now we actually get some real results. This is what it looks like. So this is for the for loop case. We have CPUs on the bottom and number of messages per second on the side. We can see that for low CPUs, we're getting about 6 million. Now, side note, some of you might have noticed, Phil got 10 million, I'm only getting 6. We had some slight differences in number of bytes sent and stuff like that. It's in the ballpark of the same amount for now. Let's just call it that. Testing methodology changed. I also had some wrappers around things to do some extra stuff. Anyway, we started at 6 million for low CPU counts. You might notice a bit of a jump there. I'm going to completely ignore that and say it was something happening on the CPU, we'll just gloss over that for now. The point is that as the CPUs increase, we sort of head down to somewhere around 1.5 million. Put another way, that is 3 times less messages than you used to have. So that means that you ran the benchmark locally, you were getting 6 million messages a second. Suddenly, when you're running code in production, you're actually getting 3 times less throughput through your channel. Like, this was just like, whoa, that's a lot. OK? Giving some more, we had the range and the select. If we put those both on the graph, you can see that a similar thing happens. We have the loop one starts at 6, the select one starts at 3. If we can just talk about that for a second. So basically what's happening is that the loop only has 1 channel to check, whereas the select has at least 2, because you're checking, like, am I reading off the channel or am I reading the close statement? And so that's why it's basically half the speed, is that you need to do 2 things that you need to check each time it loops around. And so that's why the select one is half as much. But in general, the trend is the same. The more CPUs you add, the slower it gets. So yeah, select is slower, and select has more contention. Then I just want to briefly touch on a thing that I'm calling matched receivers. So essentially, in all of the testing that I've shown you to this point, if you had 5 Go routines sending messages, there were 5 Go routines reading messages off the queue. So what I did as some extra testing is to go and say, OK, let's assume that there's only 1 worker reading off the queue, but there's multiple sending. So the CPU count will be the number of senders, but you only have 1 worker essentially reading off the queue. And that creates an interesting graph. The point is still sort of the same, in that if you look, the ones that aren't sort of dropping down immediately are the sort of single receiver side. And what that's meaning is that you have a single worker, so that it's not fighting for the contention on that worker when it's reading messages off, whereas the one where there's as many workers as there are senders is kind of always fighting for the contention on that lock in the channel, and that's why you see that steep drop-off. Again, there's some squiggles in the lines, but we'll gloss over those for now. Cool. So said another way, having a single worker halves the contention issue, but also, like, half the point of running channels is that you have multiple workers and you can sort of churn through this work faster. You don't want to limit yourself to a single worker. Cool. Something else that some of you might be asking is, OK, but what about buffers? Like, we have these channels. All of the channels that we've seen up to this point are unbuffered channels. So a message just sits there until it's read. There's no, like, scope for waiting around a bit. So this is the point of, like, setting up all this stuff, is that now we can just add some buffers and see what it does. And it looks something like this. So the number of buffers is the different colors there. Essentially, what you can see is that as the buffers increase, we have a slight increase in the throughput. So for example, the one with 20 buffers now has a throughput at very low CPU counts of close to 15 million. So the buffers obviously make a difference at the lower end of the CPU count. However, it all tends to the same number as the CPUs increase. So it doesn't matter if you have buffers or not, you still end up with the same problem that, in this case, for 20 buffers, it's actually a lot worse, because you're going from 15 million odd all the way back down to 1. So it's actually like a 15x reduction for a buffered channel. It's a bit scary. Cool. So buffers buy some headroom, but it's basically all downhill as you increase the CPUs. So for those of you that have fallen asleep, here's a TLDR of where we got to now. With a CPU count of more than 60, channel throughput is limited to around 1 million per second. That's kind of the gist of what you need to know. And that's about a 3x decrease from, like, what you would have started at if you were running the benchmark on your laptop. Right. Now, I don't want this to all be doom and gloom and, like, don't use channels anymore. So what are some of the possible solutions that we could have to this? But unfortunately, it's more like solutions, because none of them is like, oh, you just fix this one thing and everything's sorted. And It's more about sort of going, OK, this is what my code looks like, and this might work for me, but it might not work for you. And so everybody's going to have their sort of their own way of solving this. And even solving it is sort of like, have you solved it, or have you just worked around the problem for now? Because in my mind, solving it would sort of be like, OK, it doesn't matter how many CPUs you are, the performance stays the same. So that solution doesn't exist yet, but there are some workarounds for it. So firstly, simple as go max procs. At the moment, this has worked really well for us. We just set go max procs all the way down to 32. For those of you that are doing the math, that's a quarter of how many CPUs we actually have in production. Everything still runs just as fast as it was running. In fact, faster, because you don't have the locking issue on the contention. And you still only, like your CPU metrics and stuff, we were never using that much of the CPU on these aggregator nodes. And so, yeah, this works. It's simple. Might be as simple as that for you. Obviously, playing around with the exact value and stuff could get you a bit more headroom and so on. But we'll just say, easy one to play with. If you've got multiple running, you can change each one and see which one works best for you. Cool. Something else which we played around with, which was probably a bad idea, but it was fun to try, is runtime.lockOS thread. So what the idea of this is that you can take a Go routine and lock it to a specific thread, so it doesn't jump around again. Now, there's a few problems with this. You can't specify what thread. So ideally, in an ideal world, you'd be able to say, OK, the thing that's sending messages on the channel, that's on thread X. And the thing that's reading messages is also on thread X. And so it's just like a direct line between those. They don't have to jump between threads and sort of fight for contention or anything like that. That breaks because, one, you're going to have multiple workers and multiple senders. So like, you can't lock them all to the same thread. You also have no control over like, which thread it gets locked to. So you could end up, by chance, locking everything to a single thread. And then, you might as well be running your production load on your laptop kind of thing. So not recommended, but fun to play with. This one might be contentious. Having a timeout for when you're sending messages. I don't know if anybody else does this, but if you have a blocking piece of code that is waiting to send a message on a channel, what happens if it can't send that message on the channel? Like, are you blocking all your other requests before that? And so, in a way, this was what was happening with us. And we found that like, we'd rather not stop the world waiting for a single channel that is sort of waiting for contention and all types of other issues or other issues not even related to sort of specifically the channel slowdown, but some downstream issue, and we're still just waiting for this message to get sent. So why not have a timeout there and say, if we've been waiting for too long trying to send this message on the channel, just like do something else. Either try again later, put the message back on the previous queue, throw the message away, like do something, but at least don't like stop all the other code from executing. So not something very common that you see in a lot of libraries and stuff, because essentially you have to do something with this message that might be throwing away data. But in terms of like keeping code flowing nicely, something worth considering. So as well as the Go max procs, we actually did implement this too, just as a fail-safe basically sort of thing, saying, if we get to 5 seconds and we still haven't sent this message on this channel, throw it away. Like, we don't want to be waiting that long. There's other messages in the queue that we need to get to, rather. Cool. Next one. This is more of a, what I'd call maybe a longer implementation or a heavy-handed approach also, is to sort of say, well, what if we just said we have multiple channels to send on? So there's a bit of semantics onto how you choose which channel to send on, and in this case, we're just doing like a time thing divided by the number of buffers that we have. Then we have to load that buffer, and then eventually send the message on that buffer. So you're essentially sort of splitting the problem over multiple channels. Obviously, on the worker side, you then need something that's sort of going through all the different channels. So there's like issues with this too, but you are getting rid of the fact that you're sending it to a single channel, and you're now sending it to multiple channels. It's not very pretty, but it does work. Cool. And then another approach which we tried is something, we called it buffers. Essentially what you end up doing is you take more control over the locking that you're doing. So we sort of say, define a buffer. then when we get a message, we append that message to this buffer. So you're not sending anything on the channel yet. When we get to our buffer size, which, say, for example, we set to 10, then we take that whole buffer, all 10 messages, group those together as a slice of the messages, and send those on the channel. So now your worker is not reading one message off at a time, but it reads a whole stack of 10 at a time. Obviously, there's problems with this if your channels are very slow, because now you need to wait for all 10 to fill up. But in a sort of system that's running quite quickly, it shouldn't be a problem. Why this works a bit better is that you're much more in control of the lock, and the lock is a much sort of faster. You lock here, unlock there, and all you're doing is appending to the buffer most of the time. There's no other work that's going on. Sure, you check the if statement, but most of the work is just appending to that buffer. So if that buffer is optimized and relatively small, that should be that locking operation should be quicker than the contention issues you were getting in the channel situation. Then by now, a lot of you must be screaming out containers. Why isn't this just like multiple workloads of the same thing, and then you can use up all your CPUs? And that's a fair point. There are, however, a couple of things to consider in this specific use case, and containers might work for you, in that we have those 5,000 edge cache nodes. Each of those make a connection to one of the aggregators. Now, if we were running 8 aggregators on each aggregator node, as it were now, suddenly all 5,000 servers need to be making 8 times the number of connections outwards. And so you have a lot of connections going around all of a sudden. Also, you might be running a small syslog server. Suddenly we decide, oh, we're running 10 pods for every aggregator. Suddenly we have 100 pods that are all trying to connect to your syslog server. Our syslog implementation maybe makes 8 connections. That's 800 connections that are being made to your small little VPS that's just trying to get a few logs. So, you know, trade-offs on all those. But yes, containers are certainly one of the options here. Right. Some conclusions. For those of you that are waking up again, this might look like the same slide. It is. Again, channels slow down, but there are some solutions. We'll go through this again. Go max procs, buffered channels, scaling channels, and timeouts. There are some of the links that I've been through. The QR code will take you to a thing that tells you, or that has actual clickable links, because obviously none of us can copy-paste that link. Fun story, the site that this takes you to is written in Go using embed and static and runs on the edge. There's no server behind that other than Fastly edge cache servers. And that is all that I have. Any questions? I'll go back to this one.
Hey, thanks very much. Could you expand a little bit on what you believe to be the reason why more CPUs resulted in worse throughput for the channels?
So essentially what it boils down to is that for each time you want to send a message on a channel, the CPU needs to get a lock on that channel. And with more CPUs, you have more things that are all trying to fight for that lock. And so that's what the contention issue is that all the CPUs suddenly go, I'll have it, but I'll have it. And none of them actually sort of get it immediately. In a nutshell, that's what it boils down to. I'm sure there's people here that can explain it better than that.
Lovely, thank you.
Hi. So you touched a bit on the squiggles or indifferences between the tests, and I noticed that in all of the tests there was a small uptick between 75 and 100 cores, and it was across all the individual ones. So do you have any idea what caused that?
Was that 75 and 100? I think
it was one of them. They all look the same.
Are you talking about that one?
A later one, I believe. Yeah.
That's a good question. I don't know. So I have a theory about the initial line that's sort of, I don't know, call it at about 8 or 10. And that's sort of optimized for where you're at 8 sort of CPUs, so maybe the CPUs and the number of actual Go routines, not just that you're running, but like background ones too, is sort of the same. And so it sort of makes a nice uptick there where it has exactly the right number. The one that's happening at 75 to 100, I honestly, I don't know. It could be a plotting thing. So basically, in my testing, I sort of went 1, 2, 3, 4, and then started going 8, 16. And so there might just be one where I hit exactly 92 or something, and there was a bit of a gap to the previous one, but that wouldn't explain the dip before that. So I don't know. The one thing to consider here is that these are also, they're 128 core machines, but technically it's 64 core, but with hyperthreading gives you 128. So it might be something to do with that, but I haven't looked into it much further than that.
Great, thank you.
Thank you very much. And touching on the hyperthreading bit, at least with the fat CPUs these days, they've got multiple memory domains, and also, so with the AMD ones, they've got multiple CCDs, so different chips for blocks on the physical CPU. Did you investigate trying to pin your 32-thread process to a single domain, or investigate how that affected your throughput?
No, that's actually an interesting point. I don't actually even know what the exact CPU is. They are AMD CPUs, but I don't know much more than that, if that is even, because obviously it's sort of slightly older hardware, but that is an interesting point, trying to pin those to specific cores.
Yeah, one of the things I think when the Epic Rome came out was that they were 64 cores, but with 4 CCDs, and therefore each of them had their own shared level 1 and 2 cache, I think, and then there was a shared level 3 or something like that. But yeah, there's basically 4 of them, so if you had a workload that was using all 64 cores, then depending where things were being scheduled, depending which memory domains you're crossing, and we did notice some interesting quirks about how that layout is.
But I assume, so that's not using lock OS thread then? You have to schedule some, like, outside of Go to lock those to certain
Yeah, I think
cores.
it was normally like, assuming you're running Linux, a kernel scheduler thing, say, hey, pin it to this domain and keep it fixed there.
Yeah. No, definitely something worth looking into. Thanks for that.
Cheers.
I think that's all the questions. I'll be around if you have any questions or anything, let me know.